While using neural networks, when we have to predict large numbers, the common practice is that we scale these numbers down by a scaling factor. This lecture should tell you why we actually do this. In this demo, we'll use a deep neural network in order to perform a regression on automobile prices. The idea is to predict the price of an automobile based on all its input features, such as the type of car it is, the make, model, how many engines it has, and so on and so forth. This is one of the standard tutorials that is available on the TensorFlow website, which explains deep neural networks and how to use the DNN regressor estimator. So that more of the screen is devoted to the code, I'm going to toggle the header and the toolbar within my Jupyter IPython notebook, and I'll do so in all the other demos that I'll show from here on. I'm using the TensorFlow libraries with Python version 2.7, but you might be on a higher version of Python, that is Python 3, and you know that code written for Python 3 isn't really compatible with 2.7, and this is a problem. There are some imports that you could use, those certain libraries which work the same way on Python 2 and 3. And these are the imports that I set up at the very beginning. You might need to do some additional tweaking in order to get your code to work with Python 3. You can use this website that I've displayed here on screen, pythonfuture.org, to see various compatibility issues that might arise. Here are some Python libraries that I'll need to use within my code: OS, collections, and iter tools. Then come the imports for the various scientific libraries that will be useful: NumPy, Pandas, and TensorFlow. I might not always use NumPy or Pandas, but they're always useful imports to have in case you need to do some data munging before you feed it into your machine learning model. The URL lib library from 6moves basically gives you a Python version agnostic way to access data from a site. So you can make HTTP requests without having to worry about what version of Python you're running. Extremely useful once again. Here are the version numbers for the various libraries that I use, especially for TensorFlow, because it's evolving so rapidly. By the time you see this course, you might be on a newer version. You might want to see what the changes are against this version that I'm running if you find that your code does not work. The automobile dataset that we're going to use in this deep neural network regression problem is available at the University of Chicago Machine Learning Database. This is a very popular database, and it has a variety of many interesting data sets which you can use for prototyping or just seeing patterns in different problem areas or focus areas. I definitely recommend that you check it out. The automobile dataset is available in the form of a CSV file. I'm going to download it and save it on my local machine and call it automobiles.csv. I'm going to save it in the same directory where I have this IPython notebook. You could choose to just hit this URL and download the data manually and then proceed with your machine learning model, or you can automate the process of downloading the data. Here I've automated the process. If the file does not already exist on my machine, I'm going to make a URL request to this URL path in order to download the data and then print a success message once the download has completed. Make sure that the CSV file has completed download. There you can see it within this directory where your code also lives. Once you have it here, you can go ahead with the next steps. You can also explore the file contents within this Jupyter notebook. You can see that there are a variety of different makes of cars. Alfa Romeo and Audi are what I can see on the screen. The kinds of cars, whether it's a hatchback, sedan, its mileage on the highway, mileage on city roads, and so on. Let's switch back to our code and read in this file into a pandas data frame. We need to specify the columns for the CSV file and the data type for each column, which we do in this ordered dictionary. When we are reading a CSV file, we require that the columns be ordered, which is why we use an ordered dict here. You can see all the columns and the various information that we have available: the fuel type, aspiration number of doors, the stroke of the engines, peak RPM, highway, miles per gallon, and so on. Use pandas to read in the CSV file into a data frame. If you haven't used pandas before, you should definitely check it out. It's a great library for basically dealing with tabular data in the form of rows and columns, and munging data using pandas becomes very, very simple. The read CSV method allows you to specify the column names as well as the column data types when you read in the CSV file. You can also specify how you indicate values which are not applicable or not available in your data. In our file, the question mark represents a value that is not available. df.head allows us to explore the first 5 rows of this data. When you're working with machine learning, it's always good practice to explore your data and kind of get a feel for what kind of information is available. Otherwise, you won't know what kind of information that you have in order to solve your machine learning problem. We've displayed 5 rows. Each row has 26 columns, which means there are 25 different bits of information about each car. I'm not including the column that holds the index for the data here. The df.count method, the count method on a data frame, gives you how much data is available for each of your columns. And if you notice something here, you'll see that we have 205 elements of data for certain columns, but fewer elements for other columns. That means the data for those columns are not available in some cases. Let's clean up our data here and drop all of those rows for which we don't have certain values in some of these columns. And this you can do in one shot using df.dropNA. And now if you do a df.count, you'll see that we have 159 rows for which we have complete data. This is going to be our training and validation data set. While exploring the data, I figured out that only some of these columns are really pertinent in determining the price of an automobile. I'm only interested in those columns, so I'm going to trim my data set to include just columns such as make, fuel type, aspiration, number of doors, and so on. The remaining columns I'm going to leave out of my machine learning algorithm. Construct a new data frame using these trimmed columns. df.head should now show you the new pruned dataset. This contains only those columns which we feel are relevant to our machine learning model. The objective of our deep neural network regression is to predict the price of a car based on all the input features, which is why our y variable or our label is the price. We'll now write a helper function which will split this input dataset into 3 parts: one for training, one for test, and one for prediction. It's also good practice to shuffle the data that you're feeding into your machine learning model so that there are no patterns which the machine learning model latches onto by mistake. Your data shouldn't be arranged in any predictable format. Set up a random seed and shuffle your data by calling df.sample. df.sample is what you use to sample a few rows from your data frame. The number of rows depends on the fraction that you pass in. Here our fraction is 0.8, which means it will return 80% of the original number of rows within your data frame. This 80% is chosen at random. 80% of the data that you have is the training data set. The remaining 20% forms part of our test dataset. This test dataset is what we'll use to see how well our model performs on non-training data, how well our model will perform in the real world. df.drop will remove the training data. What remains is the test data. We'll also take a small sample of the test data, which we'll use for prediction. We'll actually predict the prices of those automobiles within our prediction data and see how they match up with the actual price labels that are available to us. Once we're done with splitting the data, we leave only the features within our x variables and we extract the labels which form our y variables. This we do by using the pop method on data frames. Go ahead and return the training, test, and prediction datasets along with the corresponding y labels. Remember, the y labels are the actual price of these automobiles which are no longer present within our feature vectors. This was our helper method. Let's actually invoke this helper method and assign the training, test, x and y data to corresponding variables. Here is our ytrain.head, which is just the automobile prices. The prices for these automobiles are generally in the thousands, but you'll find that neural networks perform well with smaller numbers. So it's common practice to scale whatever number you have down during training and prediction. And once you have the final predicted values, you can simply multiply by the scaling factor to get the actual prices. Using smaller numbers allow the neural networks to train faster and they generally have better performance. Divide the Y labels for training as well as test data by this price scaling factor. If you divide by 10,000, that should make sure that most prices are within the range 0 and 1. And if they are above 1, they'll not be too large, maybe between 1 and 3 for a car up to $30,000. You can verify this is the case by simply printing out the Y values, the actual prices of the automobiles. Neural networks are more performant and they train much faster when working with smaller numbers, numbers which are within the range of 0 to 1 or maybe single digit numbers. This is why when we work with larger numbers such as automobile prices, which are typically in the thousands or the 10,000s range, we scale down this number by a normalizing factor or a scaling factor. We run this smaller set of numbers through the neural network. Training is faster, the performance of the neural network is better. Once we get the predictions, we can simply multiply by the scaling factor to get the actual prices.